Xavier Puig, who's presenting work with his co-authors, Kevin Ra, Marko, Boben, Jiaman, Tingwu, Wang, Sanja, Fidler, and Antonio Torralba on simulating household activities.
Thank you. So, hello everyone. My name is Xavier Puig, and I'm going to present our work on VirtualHome, simulating household activities via programs. This is joint work with Kevin Ra, Marko, Boben, Jiaman, Tingwu, Wang, Sanja, Fidler, and Antonio Torralba. Imagine this woman has just got a robot to help her with tasks at home. For example, make a margarita. This robot could be pre-programmed to know how to do the drink, knowing all the steps that are required to do so. But this woman and her dog's expectations are high. So now the robot needs to adapt and learn how to perform many things it was not programmed to do. So how could it do so? Well, if we humans had to learn a new task that we didn't know how to do, we'd probably go to the internet and search for information about it. For instance, if we wanted to know how to make a tea, we'll try to pull some instructions on how this is done and read through it to know how to make the tea. Now, for a robot to know how to do the task, these instructions need to be given in a language that it can understand. Notice that this description here is missing many steps that we consider common sense, but a robot needs to know in order to execute the activity. For example, for boiling water, it needs to know that it needs to grab a kettle, fill it with water, put it on the stove, and so on. Instead, we could give the robot a program containing all the steps that are required to do this activity, so that the robot could execute it and perform the task that it's asked to do. Now, these programs can be used to drive a robot to perform different tasks at home, but they are indeed more general, and they can also be used to drive an agent inside a virtual house. So by creating an environment where these programs can be executed, we can simulate complex tasks before performing them in the real world. As our first step, we aim to collect a knowledge base of diverse activities. And remember that we aim to collect this aimed at robots, meaning that we want programs with all the instructions representing these activities. Of course, we want to scale this knowledge base beyond the programming savvy grad student. So we aim to collect those tasks via crowdsourcing. And we do this in multiple steps. First, we ask people to name an activity they would typically do at home, and ask them to provide a description as if they had to teach another person to do it. On the late stage, we take this description and show it to a different worker so that they can provide a program containing all the steps so that a robot could execute it. Now, many people on Amazon don't know how to program, and this makes it a pretty challenging task. To do so, we take inspiration from Scratch, which is a programming tool designed at MIT to teach kids how to program. And the idea is that kids drag and drop blocks of instructions as if they were Lego pieces to build video games or videos. What we did was to design a programming language where each block would represent an atomic action that an agent could execute, and ask people to connect these blocks together to generate sequences of actions that could represent activities. Now, for example, for setting up a table, we'll be looking for a program like this, with all the sequences of instructions that are required. Grabbing a plate, putting it on the table, and doing it the same with a fork. It took some time and some training, but after a while, we actually managed to teach people on Amazon to program. And they actually came up with pretty complex programs. For example, for an activity such as Thanksgiving, they would give us long and complex programs depicting how to set up the table for the occasion or how to prepare the turkey. And we even got instructions on how to do research, with very detailed steps like open the Word, read from books, search on the internet. Now, the same activity can be done in multiple ways, and this is reflected in our knowledge base. These are 3 programs representing making coffee. Now, some people may like to make coffee with a coffee maker or with a kettle or with sugar and milk, and this is represented in our different programs. Altogether, our collected knowledge base contains 2,800 different programs corresponding to 600 activities. As I mentioned, each program is a sequence of steps that contain atomic actions and optionally an object that the agent interacts with. So altogether, we had 75 different actions and 300 different objects of interaction. And given these instructions, or these programs, we can compare them by comparing their instructions. And this allows us to measure similarities between the programs. So what this shows is for a subset of activities, their similarities according to how similar the programs are. So we now have our knowledge base of tasks, and our next step is to build a virtual environment where these tasks can be performed. Now, many simulators have been developed over the recent years, and most of which have been focusing on doing navigation or performing small interactions in the home. we are rather interested in an environment where agents can perform small interactions that are compounded towards everyday tasks. With that in mind, we built VirtualHome using the environment, using Unity. VirtualHome contains 6 different apartments which are fully furnished so that agents can perform the activities. Their objects are made interactable and they're animated so that they change their state when agents act on them, making for real simulations. So we now have this environment when agents can play, and we need to be able to execute the actions in our programs. So given our 75 different actions, we took 17 of them and implemented them in the environment. For an action such as walking to the bathroom, we will take one of the apartments, check where the bathroom is, and use Unity's navigation package to drive the agent towards the environment. For other actions such as interacting, like here in grabbing glass, we would compute the agent's final position to the glass and perform inverse kinematics to realize a realistic animation. And we would do similarly with other actions such as opening, sitting, and so on, where we would also animate the objects to go for realistic animations. Notice that the same action can be done in multiple ways depending on the object you interact with, such as here switching on the TV or the lights. Of course, to create a realistic simulation, we also need to encode common sense in the environment. We need to feed the environment with information about what are the object's affordances or what are their physics. We don't want the agent to break the whole kitchen while creating a coffee. And this actually pinpoints why it's important to use simulators before doing things in the real world. Similarly, if the action involves watching TV, we want to make sure that the agent sits in a sofa before watching the TV. And we also need to make sure that the agent shoots for the mouth when drinking. Now, by performing optimization across the full program, our agent can now perform the full task. But perhaps we want more than this. In the real world, we can instruct humans by telling them instructions of how to perform activities, such as my mother here in the left, or like watching TV and tweeting about this. We would like to be able to do the same with agents. We would like them to be able to show them a description of a task, or maybe a demonstration of this activity, and be able to perform the same actions that humans are doing. So we would like to take a description of a task, as general, and be able to generate the program that was creating it. Or similarly, we would like to take a demonstration of one activity, and again, generate the program that represents this activity. So let's first start on going from descriptions to actions. To do that, we will first take the description, encode each of the words using Word2Vec, and feed it into an LSTM encoder. And we will later use an LSTM decoder to generate our program, where we will predict an instruction at every time step by predicting its embedding. We will train the model using cross-entropy loss for every time step, and we will then fine-tune it using policy gradient, optimizing for 2 different rewards. First, we want our programs to be as similar as possible as the ground truth. And to do that, we measure the longest common subsequence between the predicted program and the ground truth and normalize it. The idea of this is that we don't want to penalize the model if it predicts an extra instruction, but the rest of the program is okay. Of course, we also want our programs to be executable in the environment. So to do that, we design a binary reward that tells whether our predicted program can be executed or not. Notice in this example that the program could not be executed because a fridge cannot be opened when it's already open. So here's an example of the results of our model. Given this description, walk to the kitchen and put groceries in the fridge, we'll get this program where the model is incorrectly predicting one action at the beginning, which still makes sense with our description. And because of the way we measured our similarity measure, we would get a pretty good score. Now, sometimes our descriptions are not specific enough, and this leads to programs that, while may not correspond to the ground truth, they actually make sense, such as here for listening to music. We perform quantitative analysis by computing the desired metrics, similarity and executability. On the left, we show the result by randomly sampling a program, and in the middle, our model trained using cross-entropy loss. When we fine-tune with policy gradient, we can optimize both the similarity and executability. Now, for going to videos to programs, we first have to create a data set of videos representing these activities. To do that, we take our programs and simulate them in our environments by choosing a random apartment and a random agent and adding multiple objects in the apartment, and then placing multiple cameras at different positions to generate diverse realistic videos of these activities. And because our data set is created using a game engine, we can obtain rich ground truth for our videos, including segmentation, optical flow, or timestamps of our atomic actions. To go from videos to programs, we use a similar architecture as before, but using an embedding for the video clips instead of the descriptions. To do so, we take our long video, split it into two overlapping clips, and for each clip, train a segmentation model using dilated net. We then feed this segmentation into a temporal reasoning network and predict an embedding representing the instruction of the action happening there, and use this as our embedding for every clip. So with this model, we can take one program of our activity, generate a video representing this activity, and then use the model to generate, again, one prediction that could be performed on a different environment. Notice on this example that the model is able to correctly pick switching on TV or sitting, but it's still missing the action watching TV. We somehow still need to add some common sense into the models. Now, in terms of quantitative results, our model outperforms the baselines in both metrics when using policy gradient. To summarize, we propose to represent complex activities as programs, and later designed a simulator where these programs can be executed to generate like these complex activities. We want to get diverse actions that are made at agents. So we crowdsource a data set of multiple activities with programs representing each of those activities. And using our simulator, we created videos that represent these activities. Again, we want people without any programming experience to be able to drive these agents. So we designed models that can go from descriptions or video demonstrations back to these programs. This opens up exciting opportunities for the future, including modeling social activities, which actually appeared in our programs, or creating an RL platform to learn composite tasks given our programs. Now, like many of you, our robot is also eager to go watch the World Cup. So please join him on the poster C5 this afternoon. Thank you, everyone.
Any questions? All right, while we wait for the first question, I have one. So what happens if one of the commands fails in your programs? Like, let's say the fridge door falls down.
So this is something we solved afterwards in the environment, but what we have while it's running is a checker that checks whether at each time you can execute the environment. So if the agent goes and sits in a sofa that is not facing the TV and then has to watch the TV, the program will fail. And this is what serves as the binary reward to optimize our program generation.
You showed when you built the data set that for a specific task there would be multiple programs that would be compatible with that. In your last function, executability was part of the reward, but how, for example, making a coffee, in terms of reward, how do you which one is encouraged, for example, using sugar or not using sugar? How did you integrate that in training?
So at this moment, what we try to do is to predict the program that represents the video rather than the activity. So our similarity measure is what will be checking whether our predicted program is close to what the video is representing or not.
Okay, cool. Cheers.
All right, let's thank the speaker again.